A dark shadow surrounded by fire first showed us a black hole. That historic image of M87 star was just the beginning. Now, the Event Horizon Telescope is aiming its planet-sized gaze at a new target, one far closer to home. At the very heart of our Milky Way galaxy, a silent giant named Sagittarius A star waits in the dark. This is the story of the monumental effort to photograph the abyss at our galactic core. By the end, you will understand the profound scientific revolution hiding within that next image. We are chasing a ghost that flickers and changes in minutes, blurred by a cosmic fog. What will it take to finally see the monster in our own backyard? Our galaxy's center is not a place of stillness, but a cosmic whirlpool anchored by an invisible titan. This is Sagittarius A star, a supermassive black hole residing 27,000 light-years away, deep within the constellation Sagittarius. To grasp its scale, picture our Sun. Now imagine an object with the gravitational pull of 4.3 million suns crushed into a space smaller than the orbit of Mercury. That immense, silent presence is what we call Sagittarius A star. It was not discovered by a telescope capturing light, but by listening to the universe. In the 1970s, radio astronomers detected a strange, compact source of radio waves emanating from the galactic center. They watched as stars hurtling at unimaginable speeds traced wild elliptical orbits around nothing, an empty point in space that exerted a monstrous gravitational grip. These stellar dances were the definitive proof. Sagittarius A star is the gravitational keystone of the Milky Way, the invisible hand that guides the motion of hundreds of billions of stars, including our own. Every star you see in the night sky is in some way orbiting this distant darkness. Yet for decades, it remained a ghost inferred from its effects, a silhouette sketched by the frantic motions of stars caught in its whirlpool. The challenge to actually see it, to resolve its shadow against the glow of surrounding matter, would become the next great obsession for the Event Horizon Telescope. That ghost, however, is not the same as the one we first saw. Choosing Sagittarius A star was not simply about picking the next closest black hole. It was a deliberate scientific gamble, a move to test our understanding of the universe in a completely new arena. To understand the stakes, we must contrast it with our first subject, the behemoth M87 star. That black hole is a true monster, weighing in at a staggering 6.5 billion times the mass of our Sun, but it resides in a distant galaxy 55 million light-years away. Sagittarius A star, in our own galactic backyard, is a relative lightweight at 4.3 million solar masses, but it is also 27,000 light-years away, over 2,000 times closer. This creates a fascinating cosmic coincidence, because Sagittarius A star is both much smaller and vastly nearer. Its event horizon appears almost exactly the same size in our sky as the one belonging to the far more massive M87 star. Think of it like this: hold up a dinner plate at the far end of a football field. Now hold a grapefruit right in front of your eyes. They can appear to be the same size from your perspective, even though one object is intrinsically much smaller. That is the precise situation with these two black holes. They present similar challenges to our telescope, but they are profoundly different beasts. This similarity in apparent size is what makes Sagittarius A star the perfect next target. But the differences are where the real science hides. By studying this new target, scientists are conducting the ultimate stress test for Einstein's theory of general relativity. We already saw that the theory held up spectacularly well around M87 star, but Sagittarius A star offers a radically different environment. It is a quieter, less voracious black hole, with matter trickling into it at a much slower rate compared to the raging feast surrounding M87 star. The space-time around it is being warped by gravity in a different way, at a different scale. Will Einstein's equations still predict the shape of that shadow with perfect accuracy, or will we see a subtle hint of something new, a whisper of physics beyond our current understanding? Furthermore, Sagittarius A star allows us to study the chaotic physics of accretion, the process of matter spiraling into the abyss on a human timescale. While ngEHT star changes over weeks or months, the environment around our galaxy's black hole is a frenetic dance. Gas and dust orbit so quickly that the entire scene can shift dramatically in mere minutes. Capturing this volatile activity is like trying to take a clear photograph of a spinning carnival ride. It challenges the very limits of the Event Horizon Telescope's techniques. And then there are the jets. ngEHT star famously blasts out colossal beams of energy stretching for thousands of light years. Sagittarius A star is much more subdued with only faint, sporadic outbursts. Why? What dictates whether a black hole becomes a brilliant cosmic lighthouse or a relatively quiet shadow? By comparing these two, we move from seeing a single portrait to understanding a family album, learning what traits are universal and which depend on a black hole's diet and mass. The next image is not just another picture, it is a key to a new regime of extreme physics waiting in the heart of our own galaxy. But this perfect laboratory comes with a monumental catch. Sagittarius A star is not a patient, steady subject like its distant cousin. It is a ghost in the machine, flickering and fading with a mind of its own. The primary obstacle is its quiet, chaotic nature. While ngEHT star is a voracious beast, actively devouring a thick, bright disk of matter, our galactic center's black hole is on a meager diet. Its accretion flow, the stream of gas and dust spiraling inward, is faint and wispy. This makes it incredibly difficult to see against the darkness of space. To make matters far more complex, this tenuous glow is not stable. It changes rapidly on timescales of mere minutes. The hot gas whips around the event horizon at nearly the speed of light, creating a turbulent, ever-shifting ring of light. For the Event Horizon Telescope, this is like trying to take a sharp, detailed photograph of a wisp of smoke caught in a hurricane. The target itself is dissolving and reforming before your eyes. Capturing a single, coherent snapshot requires not just incredible resolution, but also incredible speed, a feat akin to freezing the motion of a hummingbird's wings with a camera the size of our planet. And the challenges do not end there. Between us and the galactic center lies 27,000 light-years of interstellar space, filled with a fog of dust and ionized plasma. This material acts like a lens of frosted glass, scattering the delicate radio waves emitted by Sagittarius A star. The sharp signals that left the event horizon arrive at our telescopes on Earth blurred and smeared, as if we are trying to read a street sign through a heavy downpour. This scattering effect distorts the image, forcing scientists to develop sophisticated new algorithms to digitally clean the signal, to peel back the layers of cosmic fog and reveal the true shape hidden beneath. So the goal is clear: photograph a faint, rapidly changing shadow, seen through a blurry, turbulent atmosphere from a distance of 27,000 light-years. This sets the stage for an immense technical challenge, one that demanded the Event Horizon Telescope to evolve. The sheer audacity of this challenge demanded a tool of equal ambition. To see the unseeable, scientists did not build a bigger telescope. They built a smarter one. They transformed our entire planet into a single, gigantic eye staring into the abyss. This is the Event Horizon Telescope, or ngEHT, and it is not one instrument you can point at the sky. It is a symphony of coordination, a global network of the world's most sensitive radio telescopes, all working in perfect unison. From the high deserts of Chile to the volcanic peaks of Hawaii, from the frigid expanse of the South Pole to the mountains of Spain and Arizona, these individual dishes all turn toward the same point in space at the same exact moment. Individually, each telescope is powerful, but together, through a technique called very long baseline interferometry, they become something else entirely. They become a virtual telescope as large as the Earth itself. Think of it like this: if you had only one small piece of a giant, broken mirror, you would see just a blurry, fragmented reflection. But if you could collect all the scattered pieces, carefully align their edges, and combine their light, the full, clear image would suddenly snap into view. The ngEHT does precisely that with radio waves. Each telescope in the network acts as one small piece of that giant mirror, collecting the faint whispers of radio light coming from the edge of the black hole. But to combine their signals, they must be perfectly synchronized, as if they were all a single, seamless instrument. This is where the magic happens. At the heart of every observation is a set of the most precise clocks ever made, atomic clocks so accurate they would not lose a second in millions of years. These clocks are installed at every telescope site. When an observation run begins, each dish records the incoming radio waves along with the exact nanosecond precise time stamp from its local atomic clock. They are not physically connected by cables, which would be impossible across oceans and continents. Instead, they are connected by time itself. Later, the mountains of data recorded on thousands of heavy hard drives are physically flown to central supercomputing facilities. There, the time stamps from the atomic clocks allow scientists to line up the signals from every telescope with perfect alignment, as if they all arrived at a single Earth-sized dish at the same instant. It is a global digital reconstruction of starlight. This painstaking process synthesizes a virtual lens with a diameter equal to the widest separation between any two telescopes in the network. For Sagittarius A star, that meant a telescope effectively the size of our planet, granting it the incredible resolution needed to spot a donut-shaped ring of hot gas only about 50 micro-arcseconds across in our sky. To understand that scale, it is the equivalent of seeing a bagel on the surface of the moon from Earth, or reading the date on a coin from 10,000 miles away. This planet-sized eye staring through the cosmic fog is our only hope of bringing the ghost at our galaxy's heart into focus. But even this monumental achievement required a crucial, final ingredient to complete the picture. Atomic clocks and global coordination gave us a single, fleeting glimpse, but a ghost that flickers demands more than a snapshot. The Event Horizon Telescope is not a finished instrument. It is a living, evolving entity, constantly pushing its own limits to chase a clearer, faster, and ultimately moving picture of the abyss. To truly see Sagittarius A star, scientists knew they had to upgrade the entire system. The first major leap was expanding the virtual mirror itself. New telescopes have joined the global array, each one strategically placed to fill critical gaps. The Greenland telescope, perched on the ice sheet's stark expanse, provides a crucial northern baseline. In the French Alps, the powerful NOMA array, with its multiple dishes acting as one, adds immense sensitivity. These new eyes do more than just make the virtual telescope bigger. They make it denser, filling in the missing pieces of the planetary mirror. Think of trying to recognize a friend's face from a handful of scattered puzzle pieces versus having most of the pieces neatly connected. More telescopes mean more connections, which translates directly into a sharper, more reliable image, one far better at cutting through the blurring fog between us and the galactic center. But a sharper mirror is only part of the solution. Remember the problem of speed. Sagittarius A star's chaotic glow changes in minutes, while the original ngEHT observations took many hours, essentially smearing that frantic motion into a single, static blur. To freeze that motion, the network needed a faster shutter speed. This is where a second, less visible upgrade comes in, increasing the observing bandwidth. In simple terms, bandwidth is the amount of data the telescopes can swallow per second. By dramatically widening this data pipe, the ngEHT can capture vastly more information in a much shorter time. It is the difference between an old camera that needs a long, slow exposure to gather enough light and a modern high-speed camera that can capture a single droplet of water in mid-splash with perfect clarity. With this upgrade, the network can now take multiple rapid-fire snapshots throughout a single observation night, building up a sequence of images that could, for the first time, show the turbulent flow of matter around the black hole as it happens. Yet even this torrent of raw data is useless without the final, crucial ingredient, new algorithms. The scattered, noisy signals from the telescopes are not a picture. They are a monumental cryptographic puzzle. To assemble them into an image, scientists use sophisticated software, and for Sagittarius A, they had to invent entirely new methods. These algorithms must now perform a kind of cosmic forensic reconstruction. They have to account for the rapid changes in the source, untangle the scattering from interstellar fog, and resist the human bias of wanting to see what we expect to see. Some of these new tools work by simulating millions of possible black hole movies that could have produced the observed data, then selecting the most plausible ones. The goal is no longer just to produce a single iconic image, but to reconstruct a dynamic process to turn a portrait into a biography. This evolving toolkit of new telescopes, faster data, and smarter software is what transforms the ambition of a movie of a black hole from science fiction into an imminent reality. It is a relentless engineering pursuit, all focused on one objective: to watch the silent giant at our galaxy's heart not as a statue, but as a living, breathing entity. And when we finally achieve that moving picture, we will be witnessing something far stranger than mere orbital mechanics. The ultimate test arrived in the chill of April 2017. For 5 precious nights, the entire planet held its breath as the Event Horizon Telescope performed its most daring feat yet. In an unprecedented act of cosmic multitasking, the global array simultaneously fixed its gaze on 2 targets. One eye stared 55 million light-years away at the calm, predictable giant ngEHT star. The other peered into the chaotic, flickering heart of our own galaxy, directly at Sagittarius A. This was not merely an observation run. It was a meticulously choreographed ballet of technology, timing, and sheer luck. Every single telescope site, from the thin air of the Atacama Desert to the frozen plateau of the South Pole, needed absolutely perfect weather. A single storm cloud over one dish, a gust of wind too strong for another, could ruin the delicate synchronization for the entire network. The universe for once complied. The skies stayed crystal clear across the globe. As Earth turned, each telescope locked onto its target, its atomic clock ticking with unfathomable precision, its hard drives whirring as they began to fill. For 10 hours each night, they drank in the faintest whispers of radio light emanating from the edges of 2 different abysses. The result was a flood of information so vast it defies everyday understanding. The campaign collected petabytes of raw data. To put that in human terms, a single petabyte could hold over 200,000 DVDs worth of movies. The entire haul from that run filled thousands of heavy, custom-built hard drives, which were then physically packed and flown to just 2 supercomputing centers on opposite sides of the planet. This was data too precious and too voluminous to ever send over the internet. It had to travel the old-fashioned way by jet plane, a modern-day treasure hunt where the gold was encoded in strings of ones and zeros. With the data secured, the processing began and a clear divergence emerged. The data for the massive, steady ngEHT star, while immensely complex, was a solvable puzzle. Its image came together, revealing that now iconic fiery ring in 2019, a triumph that shook the world. But the data for our own galactic center for Sagittarius A told a different story. It was a cacophony, a jigsaw puzzle where the pieces kept changing shape. The very turbulence and rapid flickering that makes Sagittarius A so scientifically interesting also made it a computational nightmare. While the world celebrated the first image of a black hole, a separate, even more daunting challenge was just beginning in quiet rooms, where scientists faced a mountain of data hiding a ghost that refused to sit still. The mountain of data sat waiting, a silent testament to our ambition. But those thousands of hard drives flown in from every continent contained nothing resembling a picture. Inside was a raw, chaotic sea of numbers, the faint echoes of radio waves each telescope had captured, meticulously time-stamped by its atomic clock. The first step was to make sense of this global conversation. This happens at specialized facilities called correlators, with the primary one located at the MIT Haystack Observatory. Here, banks of supercomputers perform a digital feat of synchronization. They take the data streams from, say, the telescope in Chile and the one in Hawaii, and they search for the same radio wave, checking if it arrived at both locations at the exact same moment, adjusted for the tiny delay caused by the distance between them. When they find a match, it creates a single, powerful data point. By repeating this for every possible pair of telescopes across the entire network, the correlators weave the individual threads into a coherent fabric of information. Yet, even this processed data is not an image. It is more like a sparse set of measurements, a handful of precise notes about the shape of something we cannot directly see. The problem is our planet-sized telescope has gaps. We only have dishes in specific locations, not a continuous, solid mirror covering the entire Earth. This leaves holes in our data, missing pieces of the puzzle. Filling in those gaps to reconstruct a plausible image is where the true magic and the immense challenge begins. Teams of scientists use families of complex algorithms, each with different assumptions, to solve this inverse problem. Given our limited measurements, what is the most likely source in the sky that could have produced them? To navigate this, they turn to a technique akin to crowdsourcing reality. They generate not one, but hundreds of thousands of simulated black hole images, each with slightly different properties. Maybe the ring is thicker here or brighter there, or the central shadow is a different size. They then ask which of these countless simulated images, when processed through a virtual model of our gap telescope, produces data that looks most like the actual data we collected from Sagittarius A. The algorithms iteratively guide themselves, comparing simulations to reality, slowly converging on a family of images that are all consistent with the signals we captured. The final result is not a single, definitive photograph, but a set of probable portraits. It is a statement that says, given what we measured, the black hole at our galactic center most likely looks like this. This statistical portrait is how we pull a ghost from the noise, transforming a deluge of numbers into a possible glimpse of the abyss. That ghost, once reconstructed, will paint a portrait unlike any other. Theorists armed with supercomputers have spent years simulating the probable face of Sagittarius A, and their predictions are breathtaking. The image should reveal a structure both hauntingly familiar and strikingly alien. At its heart will be a dark void, the black hole's shadow. This is not the event horizon itself, but the absence of light from behind it, a silhouette cast by gravity so intense it swallows even the paths of photons. Surrounding this central darkness will be a brilliant, fiery ring of light. This is the photon ring, the final orbit where light itself is forced to circle the black hole before either plunging in or escaping to our telescopes. But this ring will not be a perfect, symmetrical donut like a cosmic signet ring. It will be lopsided, a crescent of blazing light. One side will appear dramatically brighter than the other. This dazzling asymmetry is a direct signature of relativistic effects, a visual proof of Einstein's theories in action. The matter whipping around the event horizon at nearly light speed creates an effect called Doppler beaming. The side of the ring spinning toward us has its light boosted and focused, appearing brilliantly hot. The side spinning away has its light stretched and dimmed, receding into a faint, cooler glow. This creates a mesmerizing, unbalanced halo of fire. Furthermore, the entire ring may appear tilted or warped. Its orientation in the sky depends on two crucial factors we do not yet know precisely: the black hole's own spin and our viewing angle from Earth. Is Sagittarius A star a rapidly spinning vortex, dragging the fabric of space-time around with it like a cosmic whirlpool? Or is it a more sedate, non-spinning sphere of darkness? The spin would warp the photon ring, squeezing it on one side. And are we looking at it nearly face-on, like a bullseye, or is it tilted, presenting more of a skewed ellipse? The precise shape of that bright ring will answer these questions. Comparing it to the iconic image of M87 star will be revelatory. That distant giant showed a remarkably symmetric ring, suggesting we are viewing it from a nearly face-on perspective, and its immense, steady feast of matter created a more uniform glow. Sagittarius A star's portrait will be its wild, dynamic cousin, fainter, more turbulent, and marked by that unmistakable, brilliant crescent. It will look less like a serene halo and more like a flaming, lopsided eye staring back at us from the galactic core. These speculative animations, born from billions of supercomputer calculations, give us a preview of the violence and beauty churning just beyond the point of no return. When the real image finally resolves, it will not just be a picture. It will be a cosmic fingerprint, revealing the unique identity of the silent giant we have orbited for billions of years. A single, static portrait is only the first word in this story. The ultimate ambition, the true scientific revolution, lies in the next sentence: a movie. Not a simulation, but an actual video constructed from real observations, showing the chaotic dance of matter around Sagittarius A star as it happens. This is the frontier. To achieve it, we must move beyond the limits of our planet. The current Event Horizon Telescope network, as vast as it is fundamentally constrained by the size of Earth. To gain a sharper, faster view, we must place a piece of that virtual mirror into the void. This visionary concept is called space very long baseline interferometry. Imagine adding a single radio telescope, not on a mountaintop but in orbit around Earth. The distance from that orbiting dish to a telescope on the ground could be tens of thousands of miles, instantly doubling or tripling the effective size of our virtual instrument. The resolution would become so fine it could see details on the scale of the event horizon itself, watching individual clumps of superheated gas, each larger than our sun, as they whip around the ultimate drain. This would transform our understanding from inference to direct observation. With that kind of fidelity, we could finally witness the predicted but never seen dynamics of the accretion flow. We might see bright knots of plasma glowing like embers in a cosmic wind, forming in the turbulent disk swirling around the black hole and then vanishing as they cross the event horizon. We could track their orbits, measuring not just their speed, but the precise way the black hole's ferocious gravity stretches and shears them. This would be a direct view of space-time itself being warped, a visual map of gravity's grip. We could see how matter is not just falling in, but being accelerated to nearly light speed, its light brightening and dimming with the rhythm of relativity. A movie like this would answer questions we can only guess at today. Does the accretion disk around our quiet black hole form stable structures, or is it pure chaos? How do magnetic fields, twisted into impossible shapes by the black hole's spin, launch those sporadic jets of energy? Watching these processes unfold over hours or days would turn theoretical equations into a visible, dynamic reality. It would be like the difference between studying a fossilized footprint and watching the living dinosaur take a step. This is not a distant dream. Serious proposals for a space-based component to the Event Horizon Telescope already exist, involving compact radio telescopes in high Earth orbit. The technical hurdles are immense, requiring even more precise synchronization across the vast gulf of space and revolutionary methods for handling the even greater flood of data. But the reward is a new kind of astronomy, one where we do not just photograph the monsters in the dark, but sit in the front row and watch them breathe. That brilliant, lopsided ring of fire is more than just a pretty picture. It is a cosmic gyroscope, a direct window into the black hole's hidden engine. One of the most profound secrets the next image will reveal is the spin of Sagittarius A star. Is our galactic monster a lazy, slow-turning sphere of darkness or a frenetic whirlpool, dragging the very fabric of the universe around with it? The answer is written in the precise geometry of that shadow. A black hole's spin is not like a planet's simple rotation. It is a fundamental property that warps the space-time around it in a profound way, an effect called frame dragging. Think of it like this: a stationary black hole creates a simple, deep gravitational well like a funnel, but a spinning black hole does more. It twists that funnel like a spoon stirring a thick fluid. The faster it spins, the more violently it stirs the space-time around it. This extreme distortion leaves a clear mark on the black hole's shadow and the fiery photon ring that frames it. For a black hole with no spin, the shadow is a perfect circle. But as spin increases, that circle becomes squashed, flattened on the sides. The shadow itself also shrinks slightly in size. The photon ring hugging it becomes stretched and asymmetric, its brilliant crescent growing even more extreme. The Doppler boosting, that effect making one side blazingly bright, becomes amplified by the spin as matter is whipped around even faster in the twisted space. So by meticulously measuring the exact shape, size, and brightness distribution of the ring in the new image, scientists can calculate the spin with remarkable precision. It is like deducing the speed and tilt of a spinning top by the precise, wobbling pattern of its shadow. This single measurement unlocks chapters of our galaxy's history. A fast spin would tell a dramatic story. It suggests Sagittarius A star grew primarily through steady, long-term feeding from a consistent disk of material, all falling in from the same direction over eons. This orderly diet, like water swirling down a drain, transfers rotational energy, spinning the black hole up to incredible speeds. It implies a relatively quiet, stable galactic center for billions of years. A slow or negligible spin, however, hints at a violent and chaotic past. It suggests the black hole grew through random, messy mergers with other black holes or through gulping down large clouds of gas from random angles. These chaotic events, like dumping buckets of water into a pond from all sides, cancel out rotational momentum, leaving the giant sluggish. It paints a picture of a galactic core that was once a tumultuous battlefield, a place of epic collisions. The spin rate also dictates the black hole's present-day influence. A rapidly spinning black hole can act as a powerful cosmic battery. The energy stored in its whirlpool of twisted space-time can be tapped to launch more powerful jets, even if they are currently faint. It defines the ultimate fate of anything that ventures too close. The point of no return, the event horizon, is closer to the center for a rapidly spinning black hole, creating a more extreme and violent environment right at the edge. So when we finally see that sharp, lopsided ring, we are not just looking at a shape. We are reading the autobiography of Sagittarius A star, written in the warped light of its own ferocious gravity. That brilliant lopsided ring is not made of fire, but of something far stranger. The faint, flickering glow we see comes from the last scream of matter as it vanishes forever. But what exactly is feeding our silent giant? The answer defies our classic imagination of a black hole feast. We might picture a dense, luminous disk of gas, like Saturn's rings set ablaze, spiraling neatly into the abyss. That is what we see around many black holes, including the mighty ngEHT star. But Sagittarius A star is different. It is on a starvation diet, consuming so little that its meal is almost invisible. The material falling toward it is not a smooth, bright river, but a sparse, superheated fog. Scientists call this a radiatively inefficient accretion flow, or a RIF. The name itself holds the key. Radiatively inefficient means it is terrible at turning gravitational energy into the light we can see. Think of a traditional, efficient disk like a bonfire. You throw on a log and it crackles, releasing bright light and heat. The disk around M87 star is that bonfire. A RIF, however, is like throwing that same log into a deep, insulated furnace. The gravitational energy is still there, the heat is immense, but instead of being released as visible light, it gets trapped within the material itself. The gas is so hot and thin that particles rarely collide to produce the brilliant glow we expect. Instead, the energy is carried inward, swallowed by the black hole before it can shine brightly for our telescopes. This is why Sagittarius A star, despite its colossal mass, is millions of times dimmer than it theoretically could be. It is a cosmic miser hoarding its energy in the dark. But within this tenuous plasma, another force takes command: magnetic fields. In the absence of frequent particle collisions, these invisible lines of force become the dominant architects of chaos. The plasma is threaded with them, and as it spirals inward, the magnetic fields are stretched and twisted into impossible knots. These tangled fields act like a cosmic scaffolding, supporting the hot plasma and controlling how it moves. They can also suddenly snap, reconnecting in violent bursts that catapult particles to near light speed, creating the sporadic flares and faint jets we occasionally detect. This magnetic maelstrom is what makes the accretion flow so turbulent and flickering. So the puzzle for the Event Horizon Telescope is profound. Can its image of the black hole's shadow and the surrounding glow tell us which model is correct? The answer is a resounding yes. The predicted appearance of the ring changes dramatically depending on the nature of the accretion flow. A classic, efficient, thin disk would produce a very narrow, sharply defined ring of light. A thick, puffy, radiatively inefficient flow would create a broader, more diffuse and wispy halo. The brightness and the level of asymmetry in that lopsided crescent also depend critically on how the magnetized plasma is moving and where it is hottest. By comparing the actual image to these detailed theoretical predictions, scientists will perform a cosmic autopsy on the accretion process itself. They will be able to measure the thickness of the flow, map where the energy is being deposited, and see the imprint of those powerful magnetic fields in the pattern of light. Solving this puzzle does more than explain why our black hole is dim. It reveals a fundamental mode of how the universe operates. Most of the supermassive black holes in the universe are likely in this quiet, radiatively inefficient state, not the brilliant, feasting one. By understanding the meal of our closest giant, we are learning the preferred diet of darkness across the cosmos. That dim, chaotic glow around our black hole holds a deeper potential for violence. While Sagittarius A star is no brilliant lighthouse like its distant cousin, it is not entirely silent. Other telescopes peering in different wavelengths of light have caught it in brief, angry outbursts. For years, the Chandra X-ray Observatory has detected sudden, powerful flares erupting from the galactic center. These are not the steady, colossal beams of M87 star, but quick, intense bursts like cosmic tempers flaring. Simultaneously, radio telescopes like the Very Large Array have spotted faint, wispy structures extending a few light years from the black hole. These are the ghostly imprints of past activity, the fading scars of small-scale jets. The evidence suggests Sagittarius A star is capable of launching relativistic jets, but they are weak, short-lived, and quickly dissipate in the dense environment of the galactic core. They are a whisper compared to M87 star's roar. This presents the Event Horizon Telescope with a tantalizing question: could it see the very moment of birth? The ultimate goal is not to image the long, fading streamers, but to peer directly at the launch pad itself. This would mean resolving the base of the jet, the region impossibly close to the event horizon where magnetic fields, twisted to breaking point by the black hole's spin, act as a cosmic railgun. Here, in a zone smaller than our solar system, particles are snatched from the swirling plasma, focused into a narrow beam, and accelerated to nearly the speed of light. Capturing this would be a monumental discovery. It would show us the engine of a galactic-scale particle accelerator in the act of firing. The image would likely show a subtle, elongated feature extending from one side of the bright, lopsided ring. This tiny wisp, this finger of concentrated energy, would be the jet's route. By studying its connection to the ring and the shadow, scientists could finally decode the launch mechanism. Does the jet shoot directly from the inner edge of the accretion flow? Is it aligned with the black hole's spin axis? How do those unimaginably powerful magnetic fields actually funnel and collimate the plasma into such a straight, focused beam? For Sagittarius A, a successful jet detection would be especially revealing. Because its accretion flow is so faint and its jets are so sporadic, seeing one would tell us these outbursts are not accidents. They are fundamental releases of pent-up magnetic energy, a direct consequence of the black hole's quiet, magnetized diet. It would prove that even the most subdued giants can, when conditions are right, become cosmic marksmen. Finding that faint finger of light would do more than complete a picture. It would connect the silent shadow to the dynamic galaxy around it, showing us how a monster too faint to see with our eyes can still reach out and shape its world. This lopsided ring of fire is more than a portrait. It is a precision instrument, a gravity lab of unparalleled power. Sagittarius A offers us the most extreme environment we can ever hope to study, a place where space and time are stretched to their breaking point. Here, we can conduct the most stringent tests of Einstein's theory of general relativity ever attempted. The predictions are precise. Given the black hole's measured mass and our estimated distance, general relativity tells us the exact size the shadow should appear in our sky. It also predicts the exact degree of that lopsided flattening caused by the black hole's spin. The Event Horizon Telescope's next image will deliver those measurements with razor-sharp accuracy. If the shadow's diameter and shape match Einstein's predictions to the letter, it will be a monumental victory, confirming that his century-old equations hold sway even in this most violent of realms. But the true revolution might lie in a mismatch. What if the shadow is just a few % larger or smaller than expected? What if its asymmetry is warped in a way that spin alone cannot explain? Such a deviation, however tiny, would send shockwaves through physics. It would be a direct signal that our understanding of gravity is incomplete. Scientists would immediately begin searching for the cause within that anomalous shadow. One tantalizing possibility is a hint of quantum gravity. At the very edge of the event horizon, where gravity is unimaginably strong yet operating on microscopic scales, Einstein's smooth description of space-time is believed to break down. It must merge with the chaotic, probabilistic rules of quantum mechanics. This merger, a theory of quantum gravity, has eluded us for a century. Could the shadow of Sagittarius A show its fingerprint? Perhaps the event horizon is not perfectly smooth, but has a microscopic, frothy structure due to quantum fluctuations. This quantum fuzz could subtly alter the path of light skimming the edge, changing the shadow's apparent size or making its edges appear less crisp than general relativity predicts. Seeing that fuzz would be like discovering the atomic texture of space-time itself. Even more exotic ideas wait in the wings. Some speculative theories suggest that what we call a black hole might not be a one-way door to nowhere, but something else entirely. Could it be an entrance to a wormhole, a tunnel through the fabric of the universe? While purely theoretical, such an object would cast a shadow with a distinct signature. Instead of a central darkness, light from the other side of the tunnel might peek through, creating a faint, secondary glow at the very heart of the shadow. The Event Horizon Telescope's incredible resolution means it could, in principle, detect such a ghostly central brightness if it existed. The implications of any deviation are profound. It would mean the laws of physics as we know them have a boundary, a place where they fray and something new takes over. It would force us to rewrite the textbooks on the most fundamental force in the cosmos. Sagittarius A is not just a distant curiosity. It is a cosmic referee waiting to show us whether our grandest theories of reality are champions or whether they must finally step aside. That silent giant does not reign alone in the darkness. To understand its true nature, we must zoom out from the event horizon and see it as the anchor of a chaotic stellar metropolis. The region surrounding Sagittarius A is one of the most extreme environments in the galaxy, a place where stars are born and die in the shadow of the abyss. Most astonishing are the S-stars, a cluster of young, massive stars whipping around the black hole in frantic, elliptical orbits. Some come perilously close, skimming within just a few billion miles of the event horizon. At their closest approach, these stars are moving at a staggering fraction of the speed of light, completing an orbit in mere human years. Their existence is a profound puzzle. How did such young stars form so deep within the black hole's ferocious gravitational grip? One leading theory is they were born farther out and then dragged inward through complex gravitational interactions, a cosmic game of billiards with stellar consequences. Their frenzied dances are not just a spectacle. By tracking their orbits with exquisite precision for decades, astronomers have performed the ultimate weigh-in, providing the most accurate measurement of the black hole's mass, the very number that tells the Event Horizon Telescope exactly what size shadow to look for. But stars are not the only visitors. In 2013, a mysterious object known as G2 made headlines as it plunged toward the black hole. Initially thought to be a simple cloud of gas and dust 3 times the mass of Earth, scientists watched, expecting it to be torn apart and create a brilliant flare as it fed the giant. Yet G2 survived its closest pass mostly intact, suggesting it was not just a cloud, but perhaps a star shrouded in dust or the result of a stellar merger. Its resilience taught us that the environment right next to the black hole is even more complex and resilient than we thought. This is where the different views of our galactic center converge into a single, breathtaking portrait. Instruments like the Chandra X-ray observatory map the hot, flaring gas. Infrared telescopes peer through the dust to track the S-stars. Radio arrays chart the larger-scale structure. And at the heart of it all, the Event Horizon Telescope aims to provide the ultimate close-up, the detailed portrait of the gravitational engine itself. By combining these vastly different observations, we are not just looking at a black hole. We are studying an entire ecosystem, seeing how the central monster's gravity, spin, and occasional outbursts sculpt the lives of everything around it. The faint shadow in the ngEHT image is the missing piece that ties the violent orbits of the stars to the quiet power of the abyss, revealing how a point of infinite darkness writes the rules for an entire stellar city. The frantic dance of stars around the void is more than a spectacle. It is a clockwork of unparalleled precision, providing a completely independent test of the monster's power. For over 2 decades, teams using giant optical telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile have tracked a handful of stars, known as the S-stars, as they whip around the galactic center. These observations have nothing to do with radio waves or black hole shadows. They rely on the simple, timeless laws of orbital motion laid down by Kepler and Newton, supercharged by Einstein. By meticulously charting the elliptical paths of these stars, noting their closest approaches and orbital periods, astronomers can calculate the mass of the invisible object they are orbiting with extraordinary accuracy. It is the same method we use to weigh the Sun by watching Earth's orbit, but pushed to an extreme. The result is a clean, elegant number. Sagittarius A has a mass of 4.3 million suns. This measurement comes from watching the outside of the gravitational whirlpool. The Event Horizon Telescope, however, probes the whirlpool's very drain. Its image of the black hole's shadow is a direct measure of the warping of space-time at the event horizon. General relativity provides the crucial link between these two perspectives. The theory gives a precise formula for a black hole of a given mass, and assuming we know our distance to it, there is a specific size its shadow should appear in the sky. So we take the mass measured by the star orbits, plug it into Einstein's equations, and get a prediction for the shadow's diameter. When the Event Horizon Telescope finally delivers its sharp, definitive portrait of Sagittarius A star, scientists will immediately perform a breathtaking cross-check. They will measure the shadow in the image and compare it to the prediction from the stellar dynamics. If the two numbers match, it will be a triumph of consistency across the cosmos. It would mean that the gravity governing the orbits of stars 27,000 light-years away is the same gravity that sculpts the edge of oblivion. It would confirm that our understanding of mass, from the calm orbits of planets to the violent fringe of a black hole, is seamlessly connected. A mismatch, however, would be equally profound. It would suggest a crack in our understanding. Perhaps the star orbits are influenced by hidden mass, like a cluster of dark matter or stellar remnants, throwing off the simple calculation. Or, more excitingly, it could mean that general relativity's prediction for the shadow size is wrong in this extreme regime. The silent dialogue between the whirling stars and the dark shadow is a conversation that tests the unity of physics itself. The portrait of the abyss was not revealed by a single scientist, but forged in a crucible of competition. Behind the scenes of the Event Horizon Telescope, a deliberate and dramatic process unfolded, one designed to protect the truth from our own eager imaginations. The petabytes of data from Sagittarius A star were not handed to one group. Instead, they were distributed to 4 completely independent teams, each working in isolation, each armed with their own custom-built analysis software or pipelines. These were not mere tools, they were different philosophical approaches to reconstructing reality from fragments. One pipeline might prioritize simplicity, assuming the black hole's surroundings are smooth. Another might be built to hunt for intricate, fine-scale structures like the faint roots of a jet. A third could use machine learning to explore millions of possibilities, while a fourth relies on stringent statistical models. They all started with the same raw signals from the global telescope array, but their journeys to an image followed wildly different paths. This separation is the bedrock of rigorous science. It is a firewall against confirmation bias, the unconscious human desire to find what we expect to see. If only one team processed the data, any flaw in their assumptions, any hidden bug in their code, could create a compelling but entirely fictional image, an artifact mistaken for cosmic truth. By sending multiple expeditions into the data wilderness, the collaboration ensures that only landmarks seen by all paths are declared real. The tension in the months following the observation was palpable. Each team worked in their own bubble, refining their algorithms, cleaning the scattered signals, and slowly coaxing a shape from the noise. They were forbidden from comparing results until the very end. The question hung over every computation: would the independent pipelines born from different minds and methods all point to the same haunting silhouette? Or would they return a gallery of different monsters, a sign that the data was too faint or the challenge too great? This was the data war, a quiet, high-stakes conflict where the only victory was consensus. When the teams finally gathered to unveil their results, the moment of truth was not about a picture, but about the convergence of 4 separate lines of evidence onto a single, inescapable conclusion. The moment of convergence arrived. After years of painstaking analysis, the 4 independent teams presented their results. The data war was over, and the victor was a singular, haunting shape. In April 2022, the Event Horizon Telescope collaboration unveiled the first ever image of Sagittarius A star. There it was, the silent giant of our own galaxy, revealed not as a point of darkness, but as a glowing, lopsided ring. The world saw the ghost finally captured. The brilliant, blurry donut matched the predictions with stunning fidelity, its asymmetric glow a perfect signature of matter whipping around at near light speed. The shadow's size aligned beautifully with the predictions from the orbiting stars, a triumphant confirmation that Einstein's gravity reigns from the calm orbits of suns to the violent edge of the abyss. This was not the end of the story, but its magnificent beginning. We had our portrait. Now the quest for the movie truly begins. That first blurry ring of fire was a revelation, but its true power lies in the ripples it sends across our understanding. Capturing the shadow of Sagittarius A star does far more than satisfy curiosity. It transforms our relationship with the cosmos, turning an abstract concept into a tangible neighbor. For the first time in human history, we can point to a specific, violent place in the sky and say, that is the monster our entire galaxy orbits. This personalizes astrophysics in a profound way. The public imagination, once captivated by artists' renderings and simulations, now has a real photograph of the engine at the heart of our own celestial home. It makes the scale of the universe feel simultaneously immense and intimately close, a paradox that inspires wonder and questions in equal measure. This cultural shift is not trivial. It seeds the next generation of scientists, engineers, and dreamers who will grow up in a world where seeing a black hole is not science fiction but a celebrated fact. For the scientific community, the success of this image is a monumental validation of the Event Horizon Telescope technique itself. Proving it could image not one, but two radically different black holes, the distant, steady giant and our own chaotic ghost, demonstrates the method's robustness. It transitions the ngEHT from a daring experiment into a reliable observatory, a new window on the universe that is officially open for business. This paves the way for an ambitious new era of comparative black hole science. With the technique proven, the collaboration can now turn its planet-sized gaze toward a catalog of other supermassive black holes. Each new portrait will add a crucial data point. How does the shadow of a black hole in a quiet, elliptical galaxy differ from one in a violent, merging pair? By building this family album, astronomers can finally categorize these giants, linking the properties of their shadows, their size, shape, and asymmetry, to the lives of the galaxies they anchor. We will move from studying individual monsters to understanding the rules of their existence. Furthermore, a sharp image of our galactic center acts as a key to deciphering the entire chaotic ecosystem around it. By precisely locating the black hole's position and orientation, we can better understand the bizarre orbits of the surrounding S-stars and the behavior of mysterious objects like G2. It provides the central anchor point for all other observations, from X-ray flares to faint radio jets, weaving disparate threads of data into a coherent story of our galactic nucleus. And as with any great discovery, the greatest outcome will be the new questions it forces us to ask. The image will certainly contain subtle anomalies, features that don't perfectly match our simulations. Does the ring's brightness have unexpected variations, hinting at new physics in the magnetized plasma? Does the shadow's edge appear perfectly crisp, or is there a faint fuzziness that whispers of quantum effects at the event horizon? Each pixel in that image is a door, and behind it lies a potential revolution waiting to be explored. That first image was merely the opening frame. The true cinematic vision of a black hole requires a telescope not just the size of Earth, but one that sees with a sharper, faster eye. This is the driving ambition behind the next-generation Event Horizon Telescope. The current network, for all its power, is sparse. Its planetary mirror has large gaps like a net with wide holes, allowing precious details to slip through. The next-generation project aims to weave a finer net. The plan is audacious yet straightforward. Add many more telescopes. Dozens of new dishes, strategically placed around the globe, will fill in those critical gaps in the virtual array. More telescopes mean more connections between them, creating a denser, more complete picture of the incoming radio waves. The result will be images with dramatically sharper resolution and far greater clarity, transforming that iconic blurry ring into a structure of intricate detail. But the upgrades do not stop there. The next generation array will also listen at higher radio frequencies. This is a crucial technical leap. Higher frequency light is less scattered by the interstellar fog between us and the galactic center. Observing at these frequencies is like switching from a standard lens to a high-quality polarizing filter, cutting through the atmospheric haze to see the true colors and contours of the landscape beneath. For Sagittarius A star, this means we could see its turbulent accretion flow not as a smoothed-out halo, but as a dynamic storm system with distinct eddies and magnetic structures churning around the event horizon. This combination, more eyes and clearer vision, will turn a portrait into an IMAX film. We could watch as individual blobs of plasma, each larger than a star, complete their final orbits in real time. We could see the magnetic field lines, those invisible architects of chaos, imprinted in the patterns of light. The goal is to no longer infer the physics, but to witness it unfolding frame by frame. And with this powerful new instrument, our gaze will extend beyond our galactic backyard. The ultimate dream target for the next generation telescope is the silent giant at the heart of the Andromeda galaxy. Known as M31, this neighboring spiral galaxy hosts a supermassive black hole of its own, one that is curiously quiet and remarkably similar in mass to Sagittarius A star. Imaging it would be the ultimate comparative study. By placing the portraits of the Milky Ways and Andromeda's black holes side by side, scientists could finally answer why some giants feast loudly while others, like ours, dine in near silence. Do they have different spins, different magnetic field structures, or is their environment the sole dictator of their behavior? Seeing another so clearly would give us the statistical sample needed to move from unique case studies to universal laws of black hole behavior. Perhaps the most tantalizing goal of all lies within the bright ring itself. Einstein's equations predict that the fiery halo we see is not a simple band of light, but a complex series of nested rings, like the ripples from a stone dropped into a pond. Closest to the shadow is the photon ring, where light has made a single, tight orbit. Fainter and narrower rings surround it, created by light that circled twice, 3 times or more before escaping. Resolving this substructure, this hall of mirrors within the glow, would be a direct map of how space-time is warped just outside the point of no return. It would be a visual measurement of the black hole's spin and mass with precision beyond anything we have today. Capturing these ghostly nested rings is the equivalent of reading the fingerprint of gravity itself. The Next Generation Event Horizon Telescope is not an upgrade, it is a transformation. It promises to shift our understanding from seeing black holes as static cosmic portraits to observing them as dynamic, evolving characters in the story of the universe. The silent movie is over, the age of the blockbuster is about to begin. Every pixel in that next-generation image will be born from a storm of calculations. Behind the iconic ring of fire lies a silent partner of unimaginable power, the global network of supercomputers and the artificial intelligence that guides them. Turning the sparse whispers of radio waves into a coherent picture is perhaps the greatest computational challenge in all of science. The raw data from the telescopes is not a photograph, it is a cryptographic puzzle with most of the pieces missing. This is where machine learning steps in, not as a futuristic concept, but as an essential, practical tool. For the image of ngEHT star, a key breakthrough came from an algorithm named PRIMO, which stands for Principal Component Interferometric Modeling. PRIMO did not invent new data. Instead, it was a brilliant teacher. Scientists first trained it on a vast library of highly realistic simulations, millions of possible scenarios of how magnetized plasma might swirl around a black hole of that mass. The algorithm learned the fundamental patterns and physics of these chaotic flows. Then, when presented with the real, gapped data from the Event Horizon Telescope, PRIMO could intelligently fill in the blanks. It asked, given what we measured and everything we know about how black holes behave, what is the most likely complete image that could have produced these signals? It was like restoring a faded masterpiece, using an understanding of the artist's style and technique to reconstruct missing brushstrokes with stunning accuracy. For Sagittarius A star, the challenge is even greater due to its rapid flickering, demanding new generations of these AI tools. They must now learn to reconstruct not a single snapshot, but a dynamic sequence, essentially predicting the most plausible movie between our sparse frames of data. This computational revolution is now being democratized. The collaboration is developing and releasing open-source software, creating toolkits that allow astronomers and even interested students around the world to work with ngEHT data. Imagine a future where a university classroom can download the same signals from the galactic center and, using publicly available algorithms, attempt their own reconstruction of the black hole's shadow. This open approach accelerates discovery, inviting fresh perspectives and diverse minds to scrutinize the universe's most extreme data. It transforms the search from a closed endeavor into a global conversation where the next key insight might come from anywhere. The supercomputer and the algorithm are the unseen lenses that focus our planet-sized eye, translating noise into revelation, one probable pixel at a time. The ring of fire we see is not just a product of telescopes and algorithms, but of human hands and shared ambition. This image was stitched together by a global village of minds. The Event Horizon Telescope collaboration is a testament to what humanity can achieve when curiosity transcends borders, involving hundreds of scientists from over 20 countries across 6 continents. Astronomers, physicists, computer scientists, and engineers, each a specialist in their own arcane field, learn to speak a common language united by a single, audacious goal. The story of this image is written in the dedication of individuals facing extremes. Engineers spent months in the brutal cold of the South Pole, maintaining delicate instruments in a place where a simple equipment failure could mean waiting an entire year for a replacement part. Theorists ran supercomputer simulations for months, only to scrap them and start over when a new piece of data suggested a different possibility. Software developers worked through countless nights, writing and rewriting the code that would teach machines to see a shape no human had ever witnessed. This was not a race for individual glory, but a slow, meticulous march toward a collective truth. The data from that pivotal observing run was so precious it was physically flown on hard drives from remote mountain peaks to central processing facilities, a modern-day relay race where the baton was a box of spinning disks. In conference rooms from Cambridge to Tokyo, scientists would debate for hours over the meaning of a single, anomalous data point, knowing that any assumption could lead the entire collaboration astray. This triumph belongs to the graduate student who noticed a subtle calibration error at 3 in the morning, to the technician who hiked through a blizzard to secure a radio dish, and to the theorist whose equations provided the map for this journey into the unknown. It is a portrait of the abyss, painted with the brushstrokes of global cooperation, proving that our deepest questions about the universe can only be answered when we look together. That portrait of our galactic core is more than a scientific trophy. It is a mirror held up to humanity itself. To gaze directly into the abyss at the heart of our own celestial home forces a profound and humbling reflection. We are the temporary inhabitants of a small, rocky world, orbiting an average star in the quiet suburbs of a spiral galaxy. And for the first time, we have turned our collective ingenuity to see the silent, gravitational monarch that rules our entire starry realm. This act bridges an impossible scale. It connects the human experience, measured in decades, to the slow, billion-year heartbeat of a galaxy. In one frame, we see both our cosmic insignificance and our extraordinary ambition. We are fleeting, yet we can comprehend the eternal. We are tiny, yet we can map the monstrous. This duality is the essence of our quest. It is not merely about collecting data on plasma physics or testing gravity. It is about fulfilling a deep, innate drive to understand the architecture of our home, to look our landlord in the eye, so to speak, and finally know its face. This understanding redefines our place. We are not just passive residents of the Milky Way, adrift on a random speck. We are now its conscious cartographers. We have pinpointed the central engine, measured its power, and begun to decipher its influence on everything from the paths of distant stars to the very potential for life in our galactic neighborhood. The black hole is no longer a terrifying abstraction, a mythic beast of destruction. It is a natural, physical phenomenon, an extreme outcome of the same gravity that holds our feet to the ground and our planet in its orbit. By seeing it, we tame it with knowledge, integrating this ultimate extreme into our story of the universe. This quest, therefore, is the highest expression of our nature. It is curiosity weaponized by cooperation, a global effort to answer questions that have haunted us since we first looked up at the starlit band of the Milky Way and wondered what lay at its heart. The image of Sagittarius A star is our answer, a message to our future selves that the universe, in all its violent majesty, is not beyond our reach to know. The journey to see our galaxy's silent heart has been a battle against cosmic noise and human limits. We began with a ghost, a faint and scrambled signal buried in a fog of interstellar dust, changing its shape in mere minutes. To capture it, we built a telescope the size of our planet, synchronized by the most precise clocks ever made, and processed its whispers with algorithms that could teach themselves to see. This was not the work of a single mind, but of a global village of scientists, engineers, and dreamers, all united by a single, profound question. What does the monster in our own backyard truly look like? The transformative power of that next image cannot be overstated. For science, it is the ultimate laboratory, a place to stress-test Einstein's equations to their breaking point and perhaps catch the first whisper of new physics. For technology, it represents a leap in how we observe the universe, turning our whole world into a single, coherent eye. And for our cosmic perspective, it does something simple yet revolutionary. It makes the abstract intimately real. We will no longer just know we orbit a supermassive black hole. We will be able to point to its portrait. This transforms our galaxy from a concept into a place with a visible, beating heart. The shadow is there, waiting in the data, and soon we may all see the heart of our Milky Way for the very first time. The final portrait of Sagittarius A star is still being developed in supercomputers around the world. But you do not have to wait for the official announcement to be part of this discovery. Look up at the night sky toward the constellation Sagittarius. Somewhere in that direction, 27,000 light-years away, the image of a lifetime is taking shape. What do you think it will show? Share your predictions in the comments below. Will the shadow be perfectly round or warped by an incredible spin? Will we see the faint root of a jet or a perfectly smooth, dark void? Your ideas fuel the public wonder that makes science so vital. To make sure you see that historic image the moment it is released, subscribe and turn on notifications. The Event Horizon Telescope collaboration will share their findings through press conferences and publications, and you can follow all the latest developments directly on their official website. This monumental achievement was only possible because of the dedication of hundreds of scientists, engineers, and staff at observatories across the globe, from the high deserts of Chile to the ice of the South Pole. We owe them our thanks for expanding the horizon of human knowledge. If this journey into the heart of our galaxy has sparked your curiosity, there is so much more to explore. Seek out the story of the first black hole image, the behemoth ngEHT star, to see how this all began. Or dive into the mind-bending physics that governs these cosmic extremes where space and time are stretched beyond recognition. The universe is full of mysteries waiting to be seen, and the next great revelation is always just over the horizon.